So in this video, I'm going to give you a crack at a couple of differentiation past paper questions that take it beyond the basic techniques of how we calculate a derivative of something and looking at maximum, minimum values and closed intervals, and look at some of the applications of it. So sketching graphs of derivatives based on the original function and using it for optimization techniques, how we make maximum, minimum values from something. So here are the couple of questions I want you to have a look at. So the first one looks at sketching graphs based on the original function. So how do we sketch the derivative of it? And the second one is quite a wordy question, but this is your standard looking type of question from an exam where it looks at optimization, maximum, minimum volumes or areas, and how we can come to these. So have a read of these, pause the video and have a crack. So the first one was looking at sketching the graph of a derivative. Now remember, sketching the graph of a derivative, we have to look for several key things about the original function. So the first thing we do is we set up our axes and we look at a couple of key things. The first of them being our stationary points, our turning points. So we've got a stationary point here at 5 on the y-axis, and we've got a stationary point here at 2. What this tells me is that these are the roots of the function when I sketch it. So this is where the functions are going to cross here, and I'm also going to have a root here at 2 for my derivative. I then look at the behaviour of the values of the function and use this to determine. So this one here, I've got a positive gradient. So everything's positive, the values are rising. So what that tells me is my derivative is positive. So the values of the function here are above the axis. So this bit is going to be positive. Now this section here tells me that I've got a negative gradient between the two roots. So it's a negative set of values. So what that means is my roots are going to be below there. So my f of x is going to be negative. But it's going to have a bit where it comes back up because I've got to get back up to this root here. What I can then do is look beyond this root. So what happens above the root at 2? Well, again, all my values are negative. My gradient is going down. So it's negative values for my derivative. So up here, I've got negative. So what that means is even though I go back up to the root at 2, I still stay negative in my y equals f dashed of x graph. So it's still going to be below this. So what that actually tells me is this point here is where the root touches and goes back on itself. So it's not a root where it cuts the x-axis. It goes back because I have to stay below the axis. So I know I'm going to be positive here, negative, negative. So that allows me to fill in the gaps and sketch my curve. Comes down here, turning point there, turns back on itself, hits the root there, and then shoots off to negative infinity. That there is my function y equals h dashed of x. We sketch it using the key bits of information. First one being the turning points. These tell you about the roots of the derivative, so where it cuts the x-axis. We then look at the signs of the gradient of the line, and that tells you about whether it's positive or negative for the derivative. Positive gradient, positive derivative, negative gradient, negative derivative, so it's below the x-axis. The second one, this was our spiel question. So again, this is a very typical type of question that you'll get in an exam in a calculator paper for when you have to apply it. Now this would be an A standard question. If you want an A and higher, this is where we need to get you. So manufacturer designs an open-ended shelter like this, subject to the following conditions. So the first one, frame of the shelter is to be made of rods of 2 different lengths. X for the top and bottom, Y for the slopes. The frame has also got to be covered by a rectangular sheet of metal, the total area of which is 24 square meters. What we need to do is first show that the total length of the rods is given by this formula here. And then what we have to do is if the rods cost $8.25 per meter, they want to minimize the production costs, should be as small as possible for the total length, find the minimum value and then the cost of the frame. Again, key thing to look for here, minimum. As soon as you see something like that with a question like this, start to think of optimization. So the first part is we want to show the total length of the rods is given by this equation here. Now, these are the two conditions we've got, so these are the two properties we have to use. First thing here is looking at the amount of rods we've got. So we want the total length. So the total length of rods is given by all the way around the edge. Now if you look at this, we've got 1x here, 1x here, and 1x here. So it's going to be 3 of the x's, but it's also going to be plus there's a y there, a y there, a y there, and a y in there. So that's 4 of the y's. So I've got 3x plus 4y. Now to get this in the form I want to somehow eliminate the 4y. And this is where this condition comes into play. It's to be covered by a rectangular sheet of metal where its total area is 24 square meters. Now, it's a rectangular bit here, so to get the area of a rectangle, what we remember is its length times breadth. Now if we look at this, the breadth could be this side here, which is my x. The length, because we've got to take into account the whole thing, will be a y going up here and a y there, so it will be 2y. So what that means is x times 2y gives me my total area, which I know is 24 square meters. So what I'm then able to do is substitute this together and change the subject of the formula to y, so I can eliminate this. What I then know is 2y equals 24 over x. Now, in the equation I've got 4y. Here I know what 2 of them is. Well, what I can do is just double this and eliminate the whole of the 4y. So if I double it, I then get 4y equals 48 over x. And I can substitute it into that equation there. So I can stick it straight back into the equation at the top. And what I can then say is my length, L, equals 3x plus the new part, which is 48 over x. And that's exactly what we were after finding out. That one there is the length of the rod. So that's part A done. Part B is this bit here. So about minimizing costs, minimum value for x for the length, and then the minimum cost of the frame. So what we want to do is figure this out. Now remember, minimum is the key word you look for. Minimum, think derivatives and optimization. So what I'm going to do for this one, for part 1, I'm going to take L and I'm going to take the derivative. Now L is this bit up here. We have to make sure this part of it is in a form we can differentiate. So we change it to L equals 3x plus 48x to the negative 1. Once we've done that, we can take the derivative. So we then know that L dashed of x equals 3 plus, well, that's negative 1, 48x to the negative 2. I can then rejig this a little bit, and I get 3 take away 48 over x squared. Now I know then, for the minimum length, that equals 0. So now it's just a case of solving it. 48 over x squared then equals 3. Rejig this about, so put the x squared up and then put the 3 back down at the bottom. And what I can say is that x squared equals 48 over 3, or 48 over 3 is 16. So x equals plus or minus 4. X equals plus or minus 4 meters. Now, again, look at this. I've got a positive 4 and a negative 4. I can't have a negative length in this, so I can eliminate the negative 4. So I can then say, right, therefore, x equals 4 meters. Now I have to show that it's the minimum. So this is where my table of values comes into play again. So I set up my table of values and I can show that it's the minimum. So my value is 4. I'm looking at 4 above and 4 below. Now again, when you set up the table, think about what we said previously in our other videos. In the derivative line, it has to be the context. So in this case, it's L dashed of x. And then we look at what the graph would look like. Now at 4, we know it's a stationary point, so we know it's 0, so we know it's flat. Let's look at what happens if we're below 4. So if we're below 4, let's say 3. I end up with 3 take away 48 over 3 squared, which is 9. 48 over 9 is bigger than 3, so 3 take that away as a negative value. So I get a negative value at that point, so it's coming down. Imagine I then go above it. So let's say 5. So I get 3 take away 48 over 5 squared. Well, that's 48 over 25, which is less than 2. So it's 3 take away a value that's less than 3. So it's a positive answer, which means it goes up. So I've got a minimum turning point. So I can then say, therefore, x equals 4 gives the minimum. It gives the minimum value. Now the rods cost £8.25 per metre. So what I can do is figure out the total length by substituting into here and then figure out what my answer is. So I know x equals 4, so my length equals 3 times 4 plus 48 over 4. Well, 3 fours are 12. 48 over 4 is 12, so it's 12 plus 12, which is 24 meters. So that's the total length. What I can then do is say, therefore, the cost is equal to this total length here, the 24 meters, times the £8.25. Plug that in your calculator and you get a total cost of £198. So that there is the cost of the minimum length of rods that they're going to need in order to make this frame. This here is a very typical optimization style question. Your maximum minimum value of a scenario that they're going to give you. And this is the ultimate goal. This is where we want to be, and this is what we want to be able to answer. We want to be able to show equations that they give using conditions in the question. Remember, if there's two conditions, you'll need them both. We then also want to be able to minimize or maximize whatever the scenario is after. So this was a minimized one. You could be looking for a maximum value for something. Same sort of idea. Then it could take this further by doing the kind of thing it's got here. What's the minimum cost of a frame? Something like that. Very, very typical that could come up in your higher examination. So make sure you're able to work to this level.